Nenny, and I'm the founder of SemiWiki.com, the open forum for semiconductor professionals. Since going online in 2011, SemiWiki.com has experienced more than 3 million users. If you're not a member of the SemiWiki community, please register as my guest. I hope to see you there. Today's webinar is titled Maximize Hardware Assurance with eFPGA IP in partnership with Achronix. In this webinar, you will learn how to maximize hardware assurance for critical IP in the semiconductor manufacturing process using eFPGA technology. Hardware assurance is of critical importance for manufacturing semiconductors in applications with heightened security requirements. You will see how eFPGAs can help to reduce the risk of critical IP getting compromised during the entire life cycle of the ASIC. The speaker today is Raymond Nason, Vice President, Chief Technologist at Achronix. He has over 25 years of experience in the eFPGA and EDA industries in various senior technical and management positions. Mr. Nason joined Achronix as Chief Software Architect to manage the software development group, define the foundations and algorithms of software system, and architect key aspects of the company's FPGA architectures. In his current role, he's responsible for the production of the company's current products and R&D of new products for future use. Okay, let's get started. Over to you, Raymond.
Thank you, Daniel. The title of this presentation is Hardware Assurance through Embedded FPGA, and the scope of this presentation is really focused on how you do hardware assurance for ASICs with critical, high-value, high-performance logic that must be protected. I will cover the application domains and threats in those application domains. I will talk a little bit about the supply chain issues and what Embedded FPGA solves in terms of hardware assurance. I will talk about hardware benefits of embedding embedded FPGAs into ASICs, the protection of that embedded FPGA IP, the availability of that embedded FPGA IP, and some conclusions. There's a very strong and growing interest in hardware assurance. The application domains are not only limited to the traditional aerospace and defense application domains, but also to critical infrastructure that could be financial, industrial, telecom, wireless and wireline, utilities, cloud computing, and so forth. Increasingly, the hardware assurance aspects are relevant in the area of high revenue protection. And you can think about digital rights management of, for example, movies. Obviously, in the automotive domain, the safety issues where hardware assurance is of critical importance, and in the healthcare and medical domains as well, where everywhere where personal safety is at stake. The risks that are addressed with hardware assurance include industrial and defense espionage, IP theft, counterfeiting and overproduction, tampering and sabotage, personal safety liabilities, digital rights management, IP protection liabilities, and ransom attacks. I'll give you a few examples. In many cases, the hardware assurance is there to protect high revenue, for example, in inkjet cartridges, or in protecting movies from movie studios, but also IP that is available from other IP vendors. Obviously, in terms of technology, in the defense space, there are adversaries who would like to get their hands on critical IP. So the question is, if you have hardware, whenever you're doing an ASIC, is your hardware secure? Now, with plain ASICs, the security of your sensitive logic is inherently fatally exposed to current and future threats. There could be new attack methods, new analysis equipment that can do things that was unthinkable before, and during the lifetime of your ASIC. Flaws could get published openly in literature, and exploits could be posted on the internet. There could be leaks of the critical IP where the critical technology somehow ends up on the street. Adversaries and commercial competitors are already highly resourceful as it is, and it will continue to become even more resourceful with access to any aspect of the ASIC. So if they get physical aspects to any of the ASICs, even one instance, they could reverse engineer that ASIC and learn about the secret functions or figure out how the revenue functions work and then copy them. So those learnings of these product capabilities and flaws, they can compromise your own system, not just the ASIC itself, but the whole system can be defeated if somebody else figures out what its capabilities are. They could duplicate critical technology, so they could that could enable an adversary or a competitor to leapfrog its own technological deficits and quickly become a very strong competitor, or even get an edge on yourself. Once they get access to multiple instances of that ASIC, they could tamper with that ASIC, with the critical functions, and to, for example, build in kill switches, or in some other ways compromise its functionality. They could do so by adding logic to that ASIC, or replace the certain functions of that ASIC and make it do something else. There are certainly ways in which people currently protect their ASICs. You could set up a trusted supply chain. These exist, but they can only mitigate certain threats. For example, reverse engineering. Once one instance of that ASIC falls into the wrong hands, that is not something you can protect with a trusted supply chain. You have another problem with a trusted supply chain in that it only supports manufacturing nodes that are not very advanced, and it's falling further behind. This would be a problem if your ASIC really had to perform high performance functions. Furthermore, the trusted supply chain is becoming too expensive to maintain for advanced nodes, and it's going to be impossible in the future to have all contributors to that chain be trusted. There are several other techniques through which people try to protect the critical functions of their ASIC. Obfuscation, hiding, camouflaging of these critical and sensitive circuits comes to mind. However, those can be defeated now or in the future. There can be other ways in which you could make that functionality programmable in a post-silicon fashion. For example, you could add CPUs or application-specific IPs to or processors to that ASIC. However, that suffices only for the lower performance workloads and not for the high performance workloads that the ASIC may have to perform. And that is where embedded FPGAs are highly suitable for these high performance, low latency workloads. If we look at the ASIC supply chain, there are many threats that the ASIC is exposed to from the start to the end. It starts with the ASIC IP vendor, where there might be somebody who injects some malicious functionality into the IP that goes into the ASIC. At the ASIC design phase, there might be leaks of the critical design data, or there might again be a certain act of sabotage into that of that data. Then the chip will have to be made at a foundry, and again, it goes through many hands, not all of which can be protected or trusted or guarded. The chip then moves on to package assembly, and it's very difficult to ensure that at the package assembly phase, nobody's going to swap out one piece of silicon with the other and put it in the same package. Contract manufacture is where the chip goes onto boards, and again, there the product goes through many different hands, and it's going to be very difficult to make sure that nothing unauthorized is going to happen with that chip. Finally, these products in many of these domains oftentimes will be stored in storage for a very long time. And it's going to be very difficult to guard those PCBs for many years and to make sure that nobody is going to get access to them, steal one, and again, get learnings from them or mess with them. So this is all because the chip goes through many different locations. It's at many places, it's susceptible to malicious insertion of software and IP. It has to go in the global supply chain to offshore IC manufacturing and assembly and test. So in summary, the globally trusted supply chain has become impossible for advanced technology node ASICs. With embedded FPGA IP integration in an ASIC or SoC, what you do is you pretend that the block is really physically and logically like any other hard IP. The other functions in the ASIC will interact with it directly, just like it was any other block within the ASIC. The designs mapped to the embedded FPGA act like any other plain ASIC block as well. However, of course, the hardware programming is done through a bit stream, which is downloaded into the FPGA after power-up. It can do so autonomously by the embedded FPGA from an external flash memory, or it can be done through a root of trust that might be present in the ASIC elsewhere. In the end, the bit streams can be updated remotely, just like authenticated secure software executables. So what's very important here is that pre-deployment, the embedded FPGA is nothing else than an unprogrammed sea of programmable resources. It does not contain the critical design. Once deployed in the field, only then will it get programmed with the critical designs, and that limits the exposure to a very small number of protectable sources. What that then looks like is that you do not need to protect the embedded FPGA vendor. You do not need to have protection or trust at the ASIC design or at the foundry or at package assembly, contract manufacturer, and so on. What is now important is obviously that the design that gets mapped to the embedded FPGA is still protected, and that the bit stream itself is properly protected against tampering and other modifications. And what is very important now is also that the programming method is secure. But these problems are much, much easier to solve and much better contained. And again, what is important is that the critical subblock is programmed into the ASIC when deployed in the field and is not present in the ASIC during production, and so it is not exposed. Another benefit from using embedded FPGA for hardware assurance is that you can be immune to threats and that may exist in the future, and you can enable new features. So after the FPGA gets produced in the ASIC, maybe after some number of years, a new threat is detected. And you can now very quickly resolve that threat just by updating the program bitstream of the embedded FPGA in the field. There could be another threat after some other years, or after a few years later, you could even have a new feature that can be implemented with that same ASIC, thanks to the flexibility of the embedded FPGA core. So this slide shows you in the cartoon diagram the benefits of embedded FPGA. In general, with an embedded FPGA, you can do an earlier tape out because you don't have to wait for certain features to get fully defined. You can already tape it out with the embedded FPGA block in it, and then define those features that get implemented with the embedded FPGA at some later point in time. You can also address more products with the same piece of silicon. So you don't have to tape out multiple versions of that ASIC. You can now use that same piece of ASIC and same piece of silicon and program it in different ways and cover many more different products at higher volumes. And that's surely cost savings. What is of particular importance in the hardware assurance field is that you can extend the life cycle of this ASIC thanks to the embedded FPGA in it. And that is very important in very many applications where hardware assurance is important, because the lifetime of those products tends to be 10, 15, often even more than 20 years. And with the extension of the life cycle, you no longer then have to respin that ASIC because some new security threat became apparent, and you would have to fix it with that by spinning a new ASIC. You can now do that with the embedded FPGA. Now, as to whether the embedded FPGA itself is prone to malicious insertion and tampering, that is not really the case. The embedded FPGA is a highly regular structure, and any kind of modification or insertion of logic will stand out immediately. The location of how the critical IP gets mapped into the embedded FPGA is not known a priori to the attacker. So any embedded FPGA programming data is generated post-silicon. It's volatile, so once you turn off power, it's gone, and nobody can then take it to a lab and figure out how it was programmed. It is always strongly encrypted and authenticated. and it cannot be observed because there is configuration zeroization. That's to say that the configuration will be actively wiped out once power has been removed. And it also cannot be read back from the configuration storage in the embedded FPGA to some outside file for analysis. That is just simply not possible. Any attempts to tamper with the embedded FPGA itself can be detected fairly easily. There are test designs that you can then download into the embedded FPGA that are called confidence designs that will detect if any delays in the embedded FPGA have been changed or if any functional changes have been made before you download the critical IP into the embedded FPGA. And the way in which these tamper detections are done can also not be known by an attacker a priori. And on top of that, there are even ways in which you can do side channel attack detection. And those are adaptable as well. So once somebody figures out how to defeat a way in which this is done in a current version of the bitstream, all you have to do is download a new version of the bitstream that then will guard against that method as well. The programming methodology of the embedded FPGA is identical to any standalone FPGA. So what you do is you have the RTL of the functions that are to be mapped to the embedded FPGA, which then goes through synthesis, place and route tools, timing analysis, and a bit stream is generated and encrypted, which can then be downloaded into the embedded FPGA block that sits in the customer ASIC alongside the other ASIC blocks. There are in-system debugging tools available, which again are also security protected so that they cannot be used once the critical design is present in the embedded FPGA block. The tools that you can use for that, they start with synthesis tools. It provides system Verilog and VHDL. There's all sorts of other advanced methods to make sure that the embedded FPGA is very well integratable with the rest of the ASIC. Now, obviously, the programmable nature of the embedded FPGA might in and of itself introduce another attack surface. This can be very well covered by means of very strong bitstream encryption and authentication methods. With an embedded FPGA, the customer can choose their own methods themselves. These are very, very strong, mathematically proven methods. And on top of that, a customer could use their own proprietary methods that might, for example, be quantum resistant. At the end of the day, this really protects the critical design in the embedded FPGA in a way that is going through one particular gate, namely encryption and authentication gate, and is then not accessible or not crackable in any other way. This can also rely on additional methods like physically unclonable functions and other key derivation functions that cannot be known by anyone outside the ASIC maker. Now, as to whether you could have solved this with a standalone FPGA, that is possible. But at the end of the day, if you have a separate standalone FPGA sitting next to an ASIC, there's always going to be communication between the ASIC and the FPGA that might be prone to eavesdropping and sabotaging or some other attack surfaces. So the way in which you can then integrate that FPGA into the ASIC then also gives you better power, lower unit cost, much better latency, and much higher bandwidth between the high performance FPGA logic and the ASIC logic itself. Achronix provides embedded FPGA IP, and it's called SpeedCore. It is highly configurable, and Achronix is the only supplier of embedded FPGA IP and standalone FPGA parts. Both are in high volume production. The SpeedCore embedded FPGA IP is based on the Speedster 70 standalone FPGA architecture, which provides competitive, very high performance. It has the same logic, memory, DSP, and MLP blocks available, and the same ACE design flow tools are being used to program it. It's currently available in TSMC 16, 12, and 7 nanometer nodes, and we're also working on 5 nanometers at this point. Other nodes are available upon request. The IP is highly portable from one technology node to the other. The IP is delivered in GDS2 format with customized ACE and embedded FPGA development tools delivered to the customer as well, along with all the other customary hard IP collaterals. The IP itself can be configured to be large or small. The resource mixes can be varied based on the customer specification. In conclusion, the embedded FPGA IP maximizes hardware assurance of ASICs across all relevant application domains and all aspects of hardware assurance. Using embedded FPGAs to implement high-performance critical designs eliminates exposure of the critical designs to the entire supply chain. It enables the use of non-trusted chains with advanced nodes for ASICs that need to perform high-performance critical designs. It provides post-silicon flexibility to quickly deploy new features and countermeasures for future security attacks, and that goes straight to the field. Embedded FPGAs are virtually immune to undetected tampering, malicious insertion. Strong security and authentication methods protect the programming feature of the embedded FPGAs. SpeedCore is Achronix's high-performance, high-density embedded FPGA solution on advanced technology nodes. And if you have any questions about Achronix embedded FPGAs or any other aspect, please contact Achronix on the website shown on the slide. And with this concludes my presentation. Back to you, Daniel.
Thank you, Raymond. Okay, let's get started with the Q&A. First question, how is using an eFPGA for hardware assurance different than what you can do in a standalone FPGA?
Thanks, Daniel. Yeah, that's a good question. What I would say is that a common scenario is when much of the overall design, of which the critical functions are subblocks, needs to be implemented in ASIC for one or more reasons, like performance requirements, power constraints, form factor constraints, and cost constraints. In all those cases, eFPGA is an ideal way to guarantee hardware assurance by implementing the critical subblocks of that ASIC by means of an eFPGA. And such a tight monolithic integration of the critical functions with the rest of the design in the ASIC provides the lowest latency, highest bandwidth, cheapest and most flexible connectivity between the two, and the smallest attack surface. In those cases where performance, latency, bandwidth, form factor, and/or cost are not as much of a concern, one could attempt to partition the design with critical subblocks in a standalone FPGA and keep the rest in an ASIC. This would not only expose all communication between the ASIC and the critical subblocks, but also make the hardware assurance of the system dependent on the hardware assurance provisions from the FPGA vendor, whereas the ASIC designer would certainly insist to be in control of that.
Okay. Second question, how do you integrate eFPGA IP into an ASIC?
Yeah, that's a multifaceted question. As far as the front end is concerned, the functionality that will be implemented by means of the eFPGA is developed in the exact same way as if it was to be implemented as any other hard ASIC block. The RTL is no different. It's written in Verilog, System Verilog, or VHDL, or by means of MATLAB or Simulink, C, C++ by means of high-level synthesis, and so forth. The physical design aspects of an embedded FPGA block are very similar to integrated any other custom hard IP, with all the same IP collaterals like lef, def, .lib, dft, .cpm, and GDS files delivered by the eFPGA vendor. Verification is supported by simulation flows at various levels of detail, including .sdf back-orientated flows.
Okay. Another question, how is securely programming an eFPGA different than securely programming a standalone FPGA?
Yeah, that's a good question. In environments where hardware assurance is a prime requirement, ownership, encryption, and authentication of the configuration bit streams that program the programmable logic must be with the systems designer. Typically, a single root of trust in a system is a hard requirement, which is impossible to satisfy with off-the-shelf FPGAs from any FPGA vendor. In order to assure any programmable aspects of the system, like CPU cores and FPGA fabrics, the system's owner will require complete transparency into all details of any security-related aspect of the system, which an off-the-shelf FPGA vendor will not provide. With an eFPGA, the ASIC containing it will program the eFPGA in a way that's secured by the ASIC's own potentially custom or proprietary decryption and authentication methods and implementation.
Okay, here's a good one. Xilinx recently discovered the Starbleed security flaw. Would an eFPGA have been able to prevent it?
Yes, Starbleed is a good example of what is bound to happen whenever a cryptographic solution gets modified or enhanced with features that would not have been in an ASIC with an eFPGA. In this case, according to the researchers who found the flaw, the cryptographic functions themselves were not compromised. What happened is that a multi-boot feature got added, which inadvertently compromised the authentication functions in a way that was apparently virtually impossible to be aware of at the time of its design. This would very likely not have happened in a security-centric ASIC because it has almost none of the many highly complex security features requirements as a standalone FPGA, and each of which might present a backdoor sooner or later. So that is why an embedded FPGA in an ASIC is inherently more secure.
Okay, that's all the time we have today. I would like to thank you, Raymond, for your presentation and your answers to the questions. And I would like to thank everybody for participating in the SemiWiki webinar series. Have a good day.